Okay, so let's talk about the single biggest question holding back fully autonomous vehicles. How can we really trust the machines that drive us? The answer isn't as simple as just driving a whole bunch of miles. It's actually way more complex and honestly a lot more interesting.
So, picture this. You're in a self-driving car, and it suddenly just slams on the brakes for a dark shadow under a bridge. Now, is the system broken? Well, no. Actually, nothing has failed. The brakes are working just fine, all the sensors are online, and yet the car just did something totally unpredictable and, yeah, potentially dangerous. This right here, this is the core of a completely new kind of automotive danger, one that our old ways of thinking about safety were just never built to handle. To really get our heads around this new challenge, we first have to realize that the very meaning of car safety has changed. For like 100 years, it was all about making sure parts didn't break. Simple. Now we have to worry about what happens when everything is working exactly as it was designed to. And believe me, this is a huge shift for the entire auto industry. I mean, take a look here. On the left, you've got traditional safety. That's all about preventing random hardware failures, right? Like a steering component snapping. But on the right, that's this whole new world, and it's defined by a standard called SOTIF. This is all about the danger that pops up when the system is working perfectly, but its perception, its understanding of the world is flawed. Yeah, it's a mouthful, I know, but safety of the intended functionality is really just a fancy way of saying we need a safety standard for a world where sensors can be tricked and algorithms can get confused even when nothing is technically broken. It's all about managing the gray areas of machine perception. So you've got this totally new kind of danger. Where do engineers even begin? I mean, how do you prove something is safe when nothing is technically failing? Well, it turns out they have a master plan. It's laid out in that SOTIF standard, in a section they call Clause 9. This is the playbook. And it's so important to understand this. This isn't some simple checklist of tests to run. That would be completely impossible given the infinite number of things that can happen on the road. Instead, think of Clause 9 as the logical blueprint. It helps engineers build a convincing, evidence-based argument that they've really thought of everything. And this is where the whole strategy gets really methodical. Here's how they break it down. First, in step 1, you have to evaluate all the potentially dangerous scenarios. Then you get to step 2, and this is the big one, figuring out how to get enough test coverage of a nearly infinite world. Step 3 is where you define the specific evidence you need to gather. And then finally, step 4 is the justification. You have to argue why your evidence is good enough to prove the car is actually safe. So let's dig into that second objective for a second, because it's one of the biggest hurdles out there. How on earth do you test for a near infinite number of real-world scenarios? You can't possibly drive in every city, in every kind of weather, with every single thing that could possibly happen on the road. The answer isn't just to test more, it's to test smarter. And a huge part of that solution came from a German research project called Pegasus. They came up with this brilliant way to structure all the chaos of the real world into pieces you can actually manage. And this table just shows how brilliantly they do it. Engineers can basically create an endless list of super complex test scenarios by just picking and choosing from each layer. So, for example, they can take a sharp blind curve from layer 1, maybe combine that with a faded stop sign from layer 2, then add a pedestrian stepping out from between cars in layer 4, and then, just for fun, throw in the blinding glare of a sunset from layer 5, and boom, all of a sudden you have a structured, repeatable, and incredibly tough scenario to test against. But okay, even with this systematic map of the world, a huge question is still hanging out there. How do you know when you've tested enough? I mean, what is enough? This brings us to a really crucial step, turning that fuzzy idea of safe enough into a hard, justifiable number. This is where the whole abstract idea of safety gets translated into cold, hard math. Engineers literally start with a high-level goal, something like be 10 times safer than the average human driver. And they use formulas just like this one to work backwards and calculate a precise, non-negotiable performance target that the car's systems absolutely have to meet. So what does that math look like in the real world? Well, get this. That formula tells us that to prove just one of these safety targets with 95% confidence, a car would need to be tested for about 30,000 hours without a single failure. That's almost 3.5 years of nonstop driving, which just goes to show you why that old idea of just drive millions of miles is not a real strategy by itself. All right, so let's put it all together. Let's see how this entire framework, the new definition of safety, the blueprint from Clause 9, the math, how it all comes together to solve a real-world problem you've probably even heard of.
Let's talk about phantom braking. When a car brakes hard for what seems to be no reason at all. It is the perfect test case for this because, again, no part has failed. The car is just confused by what it thinks it sees.
So here's how that blueprint becomes a real action plan. First, engineers identify the triggering conditions. What's actually causing this? Things like shadows or maybe shiny seams in the road. Next, they set a validation target based on the math, a hard number, like fewer than one false braking event every 10,000 kilometers. And finally, they design very specific tests, both in simulation and on the road, to prove the system can actually meet that target. And all this work, it leads to one final critical thing. It's not about just racking up miles and hoping for the best. It's about building what's known in the industry as a safety case. And that is a comprehensive, structured argument supported by all this evidence that proves the leftover risk of using the system is acceptably low for all of us. Which really leaves us with the next great frontier. I mean, this structured, logical approach works beautifully for systems we can break down and totally understand. But as the AI in these cars becomes more of a learning black box, adapting in ways we can't always predict, how do we build a safety argument that we can still truly trust? That is the profound question engineers are grappling with right now.